them by a little tube and let them settle themselves. It's always going to be quicker to let them settle themselves. That's what the free market does when it is working. Marcin Chady says, what happens to all the photons emitted by black holes in the heat death of the universe? Well, they basically move apart from each other. The universe is expanding in the reference frame defined by the matter that created those black holes in the first place, and that means that when the black holes are emitting, the other black holes that are emitting are moving away from them. And therefore, as time goes on, when the photons cross each other, typically their wavelengths will be longer and longer when they cross each other. So they're lower and lower energy. So the total amount of energy density in one region of the universe occupied by the photons emitted by black holes asymptotically goes to zero in the future of the universe. So even though the number of photons in the universe stays the same, the density of photons and the energy per photon will both go down, so they become less and less important to the life of the universe. Okay, I'm going to again group together a bunch of questions. These are about the flow of time. Albin Varghese says, at the fundamental level, how do you view the flow of time? Is it meaningful to think of time as a sequence of quantum states in Hilbert space transitioning together, like falling dominoes moment by moment? Nobody Feels Time says, my relationship to time is variable. It must be my brain that creates this variability due to processing more intense scenarios with higher attention or focus while time passes imperceptibly while I sleep. How do you feel time is a human in terms of physics as well as in terms of philosophy? Dan O'Neill says, in your Mindscape podcast with William Egginton last year, the two of you talked about Kant's and Hume's theories of mind, contrasting Hume's reductionist view, where the mind is just a succession of sense impressions, with Kant's idea of the transcendental ego as the something that must endure through time to register those impressions. I know you don't believe in a metaphysical view of mind or self, but I wonder how you think time and the extension of brain activity through time might factor in an eventual biological account of consciousness. And finally, Sandro Suki says, your solo on complexity in the universe was great and made me think a lot. One question it prompted is about the connection between life and the arrow of time. Could we imagine some form of life existing in the absence of a local entropy gradient? More abstractly, can we imagine any kind of system that processes and takes advantage of information without such a gradient? Is life-like complexity intimately linked to the arrow of time? So there's a variety of questions here. I'm sort of doing a little bit of violence to them by squeezing them together, but they all deal with the flow of time from a purely physical perspective to a biological one. So I'm not going to try to give a comprehensive view of everyone's view. I'm just going to give you my view here, and you can do with it what you will. Time, in the way that human beings live it, comes in various guises, okay? And let's just stick to two of them. I talk about this in my book, From Eternity to Here, if you want more details. But one view of time is just a label. It's a label on the different moments. It's the label that you have when you say it is 12 o'clock, it's 12:30, it's 12:45, it's 1 o'clock, whatever. There's a sequence of events, and those events are related to each other by the laws of physics, okay? So that if you were Laplace's demon, if you did have perfect information about the universe at one time, you could predict what it would do at the next time. As a limited human being, you can predict something about what will happen at the next time. There's some continuity of the universe because of the laws of physics through time. The universe has stuff in it, and that stuff does not randomly completely rearrange itself from moment to moment in time because of the laws of physics. In fact, as we've discussed before, there's a lot more direct continuity over time because of the laws of physics than there is continuity over space. Something like the desk that is in front of me right now as I'm talking abruptly ends at some point in space. It does not abruptly end at some moment of time, right? It might eventually decay or be thrown away or be burnt or something like that, but that's still a gradual process over time, whereas it can just stop there in space. So that gives some feeling of continuity over time, even before talking about the arrow of time. Then the second notion that matters is this idea of the flow of time, this idea that at any one moment we're sort of moving in some sense through time, toward the future, away from the past. That sense is extremely ill-defined because once you start thinking about it, moving means changing your position in space as a function of time, as a function of that time variable we just talked about. So moving through time can't mean that, whatever it does mean. But there is some sense, nevertheless, that we flow through time in some sense. And the way I think about that sense is that at any one moment of time, you carry with you an impression of what the past was like, as well as a set of predictions for what the future is like. And what you're doing is you are constantly updating both those perceptions of the past and your predictions for the future. And it's that constant update which has a directionality to it, right? You can update what did happen in the past more directly than you can update what your predictions are in the future. That's what gives you the impression that time is flowing. So I very much think, to Sandro's question, that life, consciousness, thinking, all of those things very much are linked to the arrow of time. If one way of saying it very directly is to not have an arrow of time means either that you have some kind of system that is mechanically static, that is just sitting there, so there's literally no thinking going on, or you're in equilibrium somehow, right? You're in thermal equilibrium, and you don't have any complex organisms that can possibly think or process information. So I think it's kind of trivially true that you need a departure from equilibrium in order to be anything that would qualify as life in the ordinary sense. It's additionally true, although a little bit less trivially, that living beings take advantage of that departure from equilibrium. They take advantage by using the free energy around them to survive and persist, and also by collecting information around them in a way that is only made possible because entropy is increasing over time, okay? So I think that, I don't know if that answered everyone's questions. Maybe Dan's questions about Kant and Hume are a little bit more specific. He says, I wonder how you think time and the extension of brain activity through time might factor in an eventual biological account of consciousness. I hope that I gave you the impression it's centrally important in an eventual biological account of consciousness. Now, beyond saying that it's centrally important, how specifically will it arise in that ultimate account? Yeah, I don't know what that ultimate account is, so I can't say too much specific about that. Brendan Barry says, can you discuss how many worlds localizes the measurement of distant entangled particles? Is it wrong to think of the wave function as branching when the particles become entangled? If many worlds does make entanglement local, shouldn't the non-locality of other quantum mechanical interpretations, shown in tests of Bell's inequality, be large experimental evidence in favor of many worlds? So I don't think so, for a couple of reasons here. For one, it is wrong to think of the wave function as branching when particles become entangled. The wave function branches when any quantum system becomes entangled with its environment. But the word environment is crucially important there. The environment is the part of the quantum state that we don't keep track of. Once again, if you were Laplace's demon, you would never need to talk about many worlds or branching or anything like that. You would know the whole wave function of the universe. The worlds are emergent and are useful ways of talking about the universe because we have very limited, constrained views of it. And so we see branching and wave function collapse and things like that when the quantum system becomes entangled with the degrees of freedom that we don't keep track of, like the location of every photon or gas molecule in the room or something like that. If I get two quantum particles and I entangle them, but I don't entangle them with the environment, so if I have just two spins and I entangle them and I can keep track of them, I don't let them bump into the environment, that doesn't branch the wave function at all. That kind of entanglement, which is usually what we think of when we think of EPR or Bell inequalities or things like that, that does not branch the wave function at all. In terms of experimental evidence, I think that you can't judge experimental evidence by saying that a certain phenomenon fits in better with the attitude of a theory one way or the other. In terms of experimental evidence that you get from testing Bell's inequality, you just have to ask, what would the other theories predict? And the answer is that other theories, all the successful theories these days, whether it's many worlds or Bohmian mechanics or spontaneous collapse, they all predict exactly the same thing for the tests of Bell's inequality. Therefore, none of them really provides you experimental evidence in favor of one over the other. Said in Bayesian terms, the likelihood function of getting that experimental outcome is the same for all of those theories. Therefore, getting that data does not distinguish between them. Perry Wan says, is there an age to any of the four forces? For example, is gravity older than the strong or weak force? If so, and gravity is 10 to the whatever weaker than the other forces, does that mean that gravity is 10 to the whatever clicks of the universal clock older? Well, yes and no. I think the bigger part is no to this particular question. For one thing, there's no universal clock, right? There's no thing ticking that everyone agrees on universally. There are convenient clocks for we human beings. We tend to think of the hypothetical clock that is at rest with respect to the cosmic rest frame when we talk about the age of the universe or things like that. But that's not super fundamental. Something that is moving very, very rapidly with respect to that cosmic rest frame would have different numbers of ticks on the clock. But I think that the impression from the question is that maybe, is gravity getting weaker over time just because it's older, just like human beings get weaker over time because they get older? No, that is not something that happens. The way that we usually think of it, and this might not be right, but the way we usually think of it, the laws of physics, whatever they are, don't change from the Big Bang to today, okay? That's the simplest hypothesis to make. It seems to be completely compatible with the data. There's plenty of ways that if they did change over time, you could have noticed before. And so until we have better reason to think otherwise, most of our credence is that the laws don't change over time. Now, the laws do change their appearance over time. For example, when a symmetry breaks, how the laws appear to us in terms of the strength of forces, the mass of particles, things like that, that can change. Famously, we think that did happen at the electroweak phase transition. We broke a symmetry. We had a symmetry of the standard model. The electroweak theory had a symmetry that we called SU2 cross U1, and that broke down to simply U1. It broke down in an interesting way, so the U1 that you get after is not the U1 you had before. The U1 you have after, the symmetry you have left over after the electron weak phase transition, is a certain combination of the SU2 symmetry you had before and the U1 symmetry you had before. But nevertheless, some symmetry went away. Some particles gained masses, like the W and Z bosons, not to mention the electron and the quarks and things like that. And therefore, in a very real sense, the weak force as we know it and the electromagnetic force as we know it came into existence at that time. Now, this time is a tiny fraction of seconds after the Big Bang, okay? It's not like it took billions of years for this to happen. It's possible that there were previous phase transitions where gravity separated from the other forces, where the strong nuclear force separated from the electroweak forces, but that's all conjectural, okay? And so both, we don't know whether it happened or not, and in a very real sense, some version of those forces were there even before that. They might have changed how they appear to us, if there were such a phase transition.
Hey, what's up?
P. Walder says, in your answers you frequently use the term good Bayesian when referring to how people should acquire knowledge. Intuitively, it does seem that, even when people don't explicitly use Bayes' theorem, a Bayes-like process is used to gather information, which brings progress in terms of an increased confidence the truth is being approached, although never actually getting to truth statements. Popperian epistemology, as I understand it, suggests that whilst a Bayesian approach might frequently be useful, it ultimately has to give way to conjecture and refutation as a truth-seeking process, because Bayesian-based processes can themselves be traced to an original guess or conjecture which forms a prior in the Bayesian process. If this is the case, can you give your thoughts on whether a greater emphasis should be placed on processes based on conjectures and refutations rather than induction? Alternatively, could Bayesian approaches be considered as part of the critical process required of conjecture and refutation? You know, I can only give my vague impressions here. I am not someone who's ever studied Karl Popper in any depth. But what I can tell you is that my opinion of the idea that we proceed via conjectures and refutations is, no, we don't. That's just wrong. That's just overly simplistic. It's not that we do conjecture. That part is absolutely true. But it's the refutation part that doesn't happen. We don't refute conjectures. We gather evidence for or against them. And you know, one simple way to see this is that sometimes you get an experiment which seemingly refutes an idea that you had, but you don't believe it because you don't think the experimenters are very good, or the experimental result is just too dramatic and you're going to wait for something else to come in. All of this is because what's really happening is that you're updating your credences, and that updating is never going to 0 or 1, okay? Now, it is absolutely true that a Popperian who is skeptical of Bayesian epistemology is right to be frustrated by the importance of priors in Bayesian reasoning, because the priors are a little loosey-goosey. People get their own priors. They're not completely objective. Tough cookies. I'm sorry. That's just how it is. I mean, they reflect the fact that different people are going to be initially, that's why they're called priors, initially more or less inclined to believe certain propositions, but then the hope is that you gather enough evidence that those initial priors go away because the evidence is pointing you in one direction or another. I don't think any of that is induction, by the way. I don't think induction is how science works or how knowledge works. Abduction is a much better way of thinking about it. Inference to the best explanation. But it's really just Bayesian reasoning one way or another. Ben Lloyd says, I tend to agree with you that the LLM architecture alone will never reach any AGI level of intelligence. I also agree with you when you say that reaching AGI is totally possible. But I'm wondering for you, why are you pretty confident that it's possible? What's your reasoning behind that? I agree with you, but I'm interested in why you and most other experts in at least somewhat relevant related fields for that question also say it is possible. I say it's possible just because I don't think intelligence is magic, right? I think it's all ultimately something that happens in physical systems, because I think that brains are physical systems. So if a brain can do it, then a computer can do it. That's literally my logic, nothing deeper than that. Notice that says nothing about how easy or hard it actually will be to achieve. Eric J. Rundquist says, since as far as I understand you don't think consciousness is an epiphenomenon, what's your best hypothesis for how consciousness affects physical events in the brain? In other words, what do you think could be the physical mechanics by which consciousness does something rather than just being along for the ride as people like Annika Harris see it? I think that consciousness is an emergent phenomenon. In the level of description, where you have people who have conscious experiences, whether or not a person is conscious of something or not plays a huge explanatory role. It affects how they behave, right? You can, if you're conscious that something has happened, you will react differently than if you're not conscious that that thing has happened. This seems perfectly obvious to me, but not because it is pushing around atoms and molecules. You're not supposed to mix levels like that. You can get into conceptual confusions when you say, you know, how does the temperature in this room affect the motion of this particular air molecule? That's just a category error, right? You're mixing up two different levels of description. I think that the table in front of me has causal powers in the universe, even even though it's just a higher level emergent thing. I could bang my head into it if I wanted to. It is holding up my computer right now, right? It clearly has causal power. It's not an epiphenomenon, but it is made of atoms. And if I want to describe the universe at the level of atoms and particles and things like that, I don't ever need to talk about the table. Likewise, I don't ever need to talk about consciousness at that level. I do need to talk about it at the higher level. Paul O says, in space, no one can hear you scream. But does dark matter scream as it gets sucked into a black hole? I am using pejorative terms here for dramatic effect. We know normal matter can emit huge amount of energy in the region of black holes, like quasars. What about dark matter? I think the simple answer is that dark matter is dark. So that's what prevents it from releasing huge amounts of energy. Actually, two things are going on. One is when ordinary matter forms an accretion disk and heats up as it falls into a black hole, the heating up, shakes up the electrons and the protons in the ordinary matter, and that shaking up gives rise to electromagnetic radiation, okay? But it gives rise to electromagnetic radiation because the particles are electrically charged, which is exactly the reason they're not dark. Particles not being dark allows them to interact with E and M, and that's what allows them to give off all this radiation, okay? And dark matter doesn't do that. Dark matter is dark, so even if it were falling into a black hole, there's no way for it to dissipate energy in the same way that a charged particle can do it. The other thing is, very little dark matter actually does fall into black holes for exactly the same reason. That ordinary matter that settles into an accretion disk, that process of settling into an accretion disk also involves electromagnetic interactions. Hydrogen atoms, or whatever atoms you have, bump into each other, lose energy, dissipate, emit photons out in the universe, and via doing that, settle into the form of an accretion disk. A dark matter particle just travels right on by. It doesn't bump into anything because it's not able to interact. So it might be lucky or unlucky enough for the dark matter particle to just smack into the black hole and be absorbed. But otherwise, a dark matter particle can pass very close to a black hole and still just zoom on by the other side, as long as it doesn't literally hit it. Ordinary matter, as long as it comes close to the black hole, is going to bump into other particles of ordinary matter, lose energy, and that greatly increases the chances that it will fall into a black hole. So in the late universe especially, when matter is less dense, the overwhelming majority of mass in black holes we expect to have originated in the form of ordinary matter, not in dark matter. Jacob says, I came across an article on Hawking radiation that references the work of Michael Wondrak, Walter van Zucklecom, and Heino Falke. I don't know any of these people. Sorry about that. That doesn't mean that they're not great people. The topic was that Hawking radiation does not require an event horizon and can arise in vacuums under different geometries of curved space. Is this something that is generally understood among experts, or rather some new interpretation of Hawking's theory? If true, does this imply that we could maybe hope to detect it without needing a black hole? So I have not read this paper. I have not looked at this work, so I don't know what to say about that work in particular. I can tell you what is true about Hawking radiation. Hawking radiation, by its usual definition, absolutely does require an event horizon. You're not going to get Hawking radiation from the gravitational field of a star or a planet or anything like that. But there is another way to get something that is very much like Hawking radiation, namely if space-time is not itself static. If space-time is changing in some interesting ways, you can get radiation that is very much like Hawking radiation. In fact, my understanding is, you'll never guess who first pointed this out, but it was Erwin Schrödinger who thought about the expanding universe and labeled what he called the alarming phenomenon of particle creation in an expanding universe, which is basically, I don't think there's a direct line of referencing here, but it is essentially what we now think of as the origin of quantum perturbations in inflationary cosmology. In that case, it's not the horizon that really matters, it's just that the space-time itself is changing over time. And so the quantum fields don't settle down into a vacuum state, okay? If you have a geometry of space-time that is not changing, that is static, that is the same from moment to moment, and has no horizons, then what happens is the quantum fields just settle into an appropriate vacuum state and do not radiate. So to get radiation, you either need time dependence of the underlying geometry, or you need a horizon. Either one of those ways works, okay? But if you have neither one of those, you're not going to see any Hawking particles. Blake Stern says, what repeat killer in Columbo is your favorite? Jack Cassidy, Robert Culp, William Shatner, Patrick McGowan, or George Hamilton? Oh, I love this question, but I'm honestly not qualified enough to answer it. I think I've watched every episode of Columbo at least a couple times, at least the 70s Columbo. There's also like 80s or 90s Columbo, which I have not had the heart to see. I suspect it's not very good. You can tell me if I'm wrong about that. But I love Columbo. I love the 70s Columbo with Peter Falk, and they did have this wonderful thing where So for those of you who don't know Columbo, the TV show, Columbo is a detective, but the gimmick of the TV show is it's an hour-long episode, and the first 20 minutes or so, Columbo doesn't show up, right? They literally show you the murder. There's always a murder. And in fact, the great thing that people don't quite remember as much as they should is the murderer is always some very wealthy person or a celebrity or something like that. And they're hoist by their own petard. They think they're doing the perfect murder, and Columbo takes them down. But what you're trying to do, once Columbo does show up on the scene, as the audience member, you are not trying to figure out who did it. You know who did it. You saw it. You're trying to figure out how Columbo is going to figure out who did it, right? Because Columbo doesn't know, but he guesses pretty quickly almost all the time. And so they would have guest stars playing, the killers, etc., and the victims, and a couple of the guest stars would repeat. So Jack Cassidy is a name I recognize, as I think he was the murderer in the very first non-pilot episode of Columbo, as well as a couple episodes later. Steven Spielberg was the director of that episode. It's a classic episode. He plays an author or something like that. So I really like that one. I'm just going to guess him because I can't remember who was otherwise in these episodes. Both William Shatner and Leonard Nimoy played guest roles on different episodes of Columbo. They didn't play roles at the same time. That would have been a little weird. The other reason why I wanted to, even though I can't give you a great answer to this question, I wanted to mention it because if anyone is a Columbo fan and doesn't know, you really should be watching the current TV show Poker Face, starring Natasha Lyonne, created and directed by Rian Johnson, who also did Knives Out and Looper and things like that. And it's great. It's amazing. I mean, Natasha Lyonne is wonderful, and it is this, rather than calling it a whodunit, they call it a how catch 'em. So they show you the murder first, and then Natasha Lyonne is the informal detective. She doesn't work for the police. She's actually running away from the police, but she solves the murder every time, and it's great fun. And unfortunately, it's like on Peacock or something like that. So you have to get Peacock. I don't know. We haven't yet rationalized our way of watching TV shows here in the United States, but if you're really into it, then figure out a way to watch Poker Face. It's worth doing. And I will confess also, for those of you who are this deep into the AMA, I did ask Natasha Lyonne to come as a guest on Mindscape, because we both follow each other on Twitter back in the day, and she was interested in doing it, but she says, you have to work through my manager or publicist or whatever. When I contacted them, they ignored me. And it's fine that they ignore me. Like, I never complain when people don't appear on the podcast. I think that appearing on my kind of podcast would be relatively low impact for the popularity of her movies and TV shows than appearing elsewhere would be for the same investment of time. So I get it. But she's a very charismatic, good actor, so I recommend you to watch the show. Miran Mizrahi says, in the episode with David Tong, you said that you were going to teach yourself the algebraic approach to quantum mechanics. I'm taking myself through Susskind's theoretical minimum lectures. I recently finished the quantum mechanics one, and his approach was what I understand to be algebraic. He spoke of state vectors, expectation values, eigenoperators, etc. Wave functions were not even mentioned until lectures 6 or 7. In contrast, I had in the past tried to go through Alan Adams's quantum mechanics course at MIT, where he was a hardcore math wave functions Fourier transforms from the get-go. To me, it felt like Susskind is focusing on actually understanding how the system ticks, whereas Adams was focused on practicalities for physics students, and I never quite got it like I did with Susskind. Why so different for the same topic? What is your approach? Which would you prefer, and why? So just to let you know, Susskind's approach in the theoretical minimum is not what we were talking about when David Tong and I were talking about the algebraic approach to quantum theory. It's true that one uses algebra in quantum mechanics, no matter how you are teaching it, but the idea of algebraic quantum theory is specifically a reformulation of how quantum mechanics is presented that doesn't talk about state vectors, much less wave functions or anything like that. If you think about it, in quantum mechanics, we typically have observables like position and momentum and spin and things like that. These are implemented by operators, technically speaking. All versions of quantum mechanics use that language. You have operators, you have observables, etc. But so here's a little bit of mathematical abstraction that is kind of fun. Famously, you know that momentum and position cannot be measured simultaneously in quantum mechanics. That's the Heisenberg uncertainty principle. You could measure position, and you could then measure momentum, starting with an individual state. But if you measured momentum and then position, in other words, if you did it in the opposite order, you would get a different answer. So p times x is not the same as x times p, if you think of those as operators acting on some quantum state. And so this fact is what is called a commutation relation between x and p. And the point is, when we learn this for the first time as students studying quantum mechanics, we are presented with the idea of a state of a quantum system. You can call that state a state vector or a wave function, a vector in Hilbert space, whatever you want to call it, but there's a quantum system and it has a state. And then we act with that state with all of our different operators, like position, momentum, to be observables, and we specify these commutation relations to tell us if we did x then p, how would that be different than if we did p then x, okay? But if you're mathematically very fancy, you can take an attitude that what matters is the set of operators and their commutation relations, not the set of states that they are acting on. So think about, think about rotations in three-dimensional space, right? I can take this coffee mug in front of me, I can rotate it around the x-axis, the y-axis, the z-axis, and you can easily verify for yourself. Don't do this with a full coffee mug, but if you rotate around the x-axis and then the y-axis, you end up in a different configuration than if you rotate it around y and then x. They don't commute with each other. So to a physicist, maybe you think of this idea of rotations as something that happens to a coffee mug, okay? But the mathematicians say, I can just tell you the abstract idea of a rotation, this rotation and that rotation, and how they relate to each other, even if they're not rotating anything. It doesn't matter the thing you're rotating. What matters to the mathematician is the set of all possible rotations and how they interact with each other. That's the philosophy behind what is called the algebraic, or sometimes the C-star algebra version approach to quantum mechanics. You put the operators first and forget about the quantum states. You can still specify states, and there's a way to specify quantum states, but you don't specify them by giving a vector in Hilbert space. You specify them by saying, what would the expectation value be for all my operators? Because you're very operator-centric, okay? So anyway, that's a long-winded way of saying that the particular thing we're talking about is not the distinction between Susskind's approach and Adams's approach. Honestly, I suspect, I haven't looked at either one of these very carefully in a while, but I suspect that the difference between Susskind and Adams is just that Alan Adams is teaching quantum mechanics to physics majors at MIT, or at least at the level of students who would go to MIT. Susskind, in his theoretical minimum books, is trying to be much more understandable to a broader audience, right? So it's kind of natural that if you're not embedded in this as a student at MIT, you might find Susskind's approach more amenable to learning. That's exactly what he was trying to do, much like what I was trying to do in the Biggest Ideas in the Universe books. Henry Jacobs says, what is the relationship between moral constructivism and moral relativism? Well, I think the relationship is right there in the words. Moral relativism says that there's no objective morality, but what the moral relativism says that there are morally right or wrong things according to the views of a certain society, okay? A different society is not allowed, and this is a more controversial step, but typically it follows that you would say, like, one society doesn't get to judge the other society. If you're morally relativistic, all you can say is that within that society, a certain act is or is not moral. Constructivism says that morality is not objective, so they agree with the relativist in that, but what they say is that morality is constructed by individual people or sets of people. It could be constructed by a group, whether that's a culture or a society, or it could just be constructed by individuals, and it has no absolute claim to rightness or wrongness. It's constructed, but once you've constructed it, you've constructed it. There's nothing in moral constructivism that stops me from condemning the actions of other people who don't agree with me, right, or who are in different contexts. There's nothing about, I'm not construing morality to be something that depends on the context I'm in. I'm just admitting that morality is not out there in the world. Morality is something that is built by human beings. The obvious problem, and you should not pat yourself on the back for realizing this, because everyone knows this, about being a moral constructivist is that different people will construct different things, right? What do you do? And the mistake to a moral constructivist is to think that there needs to be some objective algorithm for answering that question. They're telling you, we admit there is no objective algorithm for reconciling moral disagreement between different agents. What they will do is talk to each other, try to persuade each other. You could try to point out that someone else's moral system that they have constructed might be incoherent. It might be based on bad logical reasoning steps from some premises to some conclusions or something like that. You would also admit that maybe you just disagree in fundamental ways. Maybe your moral premises are just different from each other. And people respond by saying, well, but that's horrible. Like, what are we going to do? And the moral constructivist says, what do you mean? That literally happens all the time. It's just the real world. You deal with it the way you deal with it in the real world. You either try to tolerate and put up with it, or if the other person's morality is so different than yours that they keep causing harm, you fight them. You try to stop them from doing it. You put them in jail or whatever. That's just what happens in the real world. So it's not like, well, I can say they're coming from a different culture. In their culture, it's okay to murder babies, so I have to put up with it. No moral constructivist thinks like that. Aaron Frankel asks a priority question. He says, I love your AMAs, would love to hear about your process for preparing to do these shows. I've heard you talk about how you pick the questions, but do you plan out your answers in advance or you just do it all on the fly in one take? Well, certainly one take. I don't do more than one take. I mean, I'm recording. It's not live, right? So if I cough or if, a disaster happens, if the phone rings or whatever, I can stop and pause and delete that part out, but I'm not going to do multiple takes for all 3 hours of the AMAs. It's not completely in the moment, in real time, because I take the questions that are asked on the AMA webpage, on the Patreon page, and I copy and paste them into a file, and then I go through and decide which ones I'm going to answer. And the process of deciding which ones I'm going to answer involves reading the questions and thinking about how I would answer them and whether I have anything interesting to say. But I don't spend too much time doing that. It would just be too much time, right? So I read the questions, kind of quickly think like, okay, what would I say to that? And then I put it in the file. And then the file is there, and I go to the file and I start talking to the microphone. I read the question in real time and provide an answer in real time. There's not a lot of preparation or planning answers in advance, like just enough of a knowledge of what the questions are so that I'm not taken by surprise when the questions appear. Patrick Lardieri says, in the June AMA, you answered a question from Michael Bright about the evolution of the wave function of a single photon. In your response, you made the claim that when your telescope detects a photon that was emitted by a quasar billions of light years away, until you detected it, its wave function was spread out all throughout the universe. This got me wondering which of the following applications of the Born rule to this event is correct. Do the Born probabilities generated from the said photon's wave function determine the chance of the telescope detecting the photon at its location? Or do the Born probabilities determine where the photon will be detected across the entire volume of its wave function once detected by the telescope? The first case seems likely to me, but I am not sure. So let's see. I think the first case is the one that we want to do here. We can simplify this, right? Forget about the fact that the quasar is a billion light years away. It doesn't matter. What if it's a meter away? Who cares? It's the same exact analysis, just the numbers are different. You're imagining some process emits a photon, and imagine that you're simplifying your life to where you know it's one photon. It's not multiple photons. And furthermore, it's emitted in a spherical wave function, so it's going off in all directions, okay? In fact, these are not unrealistic assumptions. That's something that's pretty close to what you expect to actually happen. And then a meter away from that emission of a photon, I have a detector, and the detector has some size, okay? So the wave function is moving out at the speed of light in a spherical pattern, and in one part of the size of the wave function, I don't know, some tiny fraction of a second later, okay? I'm not going to try to do the math in my head. See, I'm making these up as I go along. I'm not planning them out. Whenever the light gets to the wave front of the wave function gets to the detector, it will either collapse where the detector is, and the detector will say, I have detected a photon, or it will collapse to not being there, okay? The wave function collapses, but a collapse doesn't mean it's at a point, right? The collapse just means I've realized one of the possibilities. So there's one possibility that this photon hits the detector at some point in the detector. There's the other possibility is, no, I don't. So the rest of the wave function still exists and is still moving out in a spherical pattern minus a hole where the detector was, right? So we're imagining our detector is 100% efficient. So if the wave function at the detector is the branch of the wave function that we're in, so if the photon gets detected, it won't continue past, none of the wave function continues past the detector in that direction. So now you have a spherical wave function with a hole in it, and if you had many telescopes or many detectors arrayed all over, that would continue to happen. In fact, in the universe, in the quasar example, the photon could bump into atoms or planets or rocks or whatever all over the universe, so it becomes some much more modeled thing than the original pristine spherical wave function. And then the Born rule probability is, how much of the wave function squared is hitting the detector versus moving off in some other direction that doesn't hit the detector. Alexei Kostibas says, is there a point at which a deterministic system scales beyond what we can call practically deterministic? LLMs, of course, might be an example of something starting to get to that point. While we know exactly how they work in principle, analyzing their state to determine why they do certain things is incredibly difficult. If you incorporate a self-feedback mechanism, that gets even more difficult. I suspect a scientist would just call this a measurement problem or something, but it feels like a useful thing to admit. No, scientists are actually very, very aware of this. And in fact, there are points, it's not a single point, it depends on details, but there are points at which systems are in principle deterministic, but in practice not, okay? That's really what all of chaos theory is about. Chaos theory is about the fact that even very small errors in understanding the initial condition of a system can lead to largely different behaviors down the road, and you try to quantify that and so forth. Sometimes it's not chaotic in the literal sense because there's not an infinite amount of room, but you have something like an LLM or an algorithm where you can't tell ahead of time where the algorithm is going to go. That's actually really easy to reach. It's not hard to make a system that is deterministic in principle but unpredictable in practice. There's also, like you say, elements of feedback that come in. Jeanne Ismail, we talked to her on the podcast, has made a very big deal of the fact that even though, you are not Laplace's demon, and indeed Laplace's demon doesn't exist, you could imagine Laplace's demon outside the universe, right? If we did live in a simulation, in principle, there could be another simulation running that could say exactly what's going to happen in this universe. But you can't have Laplace's demon inside the universe, because if you are inside the universe, your choices affect what happens in the universe, and there's no way for you to carry enough information in your mind to actually predict what you yourself are going to do, okay? So it's actually a very, very practical, down-to-earth problem. Indeterminism in practice happens all the time. Wonder says, what is your favorite Jane Austen novel? I'm actually not sure why I picked this question, just to sort of mix things up a little bit, because my answer is very, very down to earth. It's very, very banal. It's Pride and Prejudice is my favorite Jane Austen novel. It's everyone else's favorite too. So some people try to say that Emma is better or whatever, but part of the joy of reading a Jane Austen novel is liking the characters. And in Emma, it's a little bit harder to like the characters. The very first Jane Austen novel I ever read was Mansfield Park, and a good friend of mine who's a big Jane Austen fan was chagrined to learn that. She's like, oh, you're never going to read another one. That's the worst one. And in part because the main character is really just not very likable. Whereas in Pride and Prejudice, all the main characters are very likable, or at least very, very entertaining. It's been interesting for me to hear reactions over the years from people who read Jane Austen and who don't like her, which is fine. You're allowed not to like her. But it indicates, that we're trained. Part of the reason why people don't like her is it's what's going to happen at the end, right? There's always a happy ending between the heroine and the hero, and they get together, etc. So, what's the point in some sense? And just asking the question reveals the assumption here that somehow the point of a novel is supposed to be the resolution of the plot. But there are other points to novels, to storytelling, to narrative more generally. The journey to get there can be interesting. And to me, what Jane Austen does better than anybody else is just follow from moment to moment in this exquisite detail what each character is thinking and reasoning and admitting to themselves, right? Neither the characters nor the narrator are completely accurate or honest about how the characters are behaving or how they're thinking, because human beings are never completely accurate or honest when it comes to that. We make mistakes, we justify things. There's a reason why Jane Austen's titles are things like Pride and Prejudice, Sense and Sensibility, right? Things that are both, have some good aspects to them, but can also be foibles taken too far. That's the joy in the novel. It's very different than reading a mystery novel where you're trying to figure out who did it. Doug Eltoft says, I understand how the free energy from the sun enables life on Earth. Was there free energy in the early universe that enabled the creation of the mass that formed into stars? What was the process that created the first mass and or energy? Well, not exactly that way, I would say. Free energy, let's back up. To a good approximation, the amount of mass in the universe is conserved. It's the same. The number of protons and neutrons and electrons in the present universe is more or less the same as it was a few minutes after the Big Bang. In the very, very early universe, maybe there were no particles like that. Maybe it was just field energy in an inflaton field or whatever. But once you get past a few minutes after the Big Bang, the matter content of the universe is more or less set. So what happens is that you rearrange that matter content. And indeed, free energy is a very subtle concept. The label isn't very good. Famously or infamously, when Erwin Schrödinger wrote his book, What is Life, he talked about free energy all the time, but he never called it that. He invented the term, I think he invented the term neg-entropy, minus the entropy. Free energy can be thought of as related to the total entropy that you could have in a system minus the actual entropy. But the point is that free energy is not like a kind of energy that brings things into existence. It's a feature of the energy that is already there, right? There's a certain amount of energy. Some of it is characterized as free energy. Some of it is characterized as dissipative energy, useless energy, right? Not free. Free doesn't mean free beer, right? Free means free to do work. It's more like free speech than free beer. It's able to do work. That's what free energy means. So free energy means low entropy energy, energy that can be put to some good use, like repairing living beings and things like that. There was an enormous amount of free energy in the early universe, but it didn't create or enable the creation of the mass that formed into stars. It helped organize the evolution of the mass that formed into stars, but the mass was always there. Sid Huff says, in your reflections on Brian Van Norden's appearance on Mindscape, at one point you used the label BC, i.e. before Christ, in reference to the era of Aristotle and other early philosophers. I also noticed that Brian himself at one point in the podcast discussion used the secular label CE, Common Era, rather than AD, Anno Domini, the year of our Lord. Do you think that these small but noticeable labeling differences are important to emphasize? Well, I think it depends on the context, whether they're important to emphasize or not. For me, I'm not going to pretend that I'm 100% consistent in this, but if I'm writing or in an academic context where we're trying to be careful, I would use CE, Common Era, or BCE, before Common Era. Those are the accepted academic labels for this way of denoting the calendar years. But in common conversation, a lot of people have never heard those labels, right? So if you're just chatting, if I'm talking into a podcast microphone, I'm more likely to use BC and AD just because I'm trying to communicate, and that's what people are used to. So unless I want to stop and explain my nomenclature, that's probably how I would go. I don't really care that much. They're just labels. It's not like if you say BC, you are admitting that Jesus Christ is the Son of God. I don't think that really logically follows. Steve Bonner says, I've read that protons and neutrons contain 3 quarks, one of each color, and a sea of quark-antiquark pairs. The term sea suggests a large number. Do we have any idea how many such pairs there are? Well, there are a lot of things that we're a little bit unsure of when it comes to the interior of a proton, the detailed quantitative structure that is in there. But this one I know the answer to, which is that there's no such thing as the number of pairs there are. When you're told that in addition to the 3 quarks, there's a sea of quark-antiquark pairs, you're being told a little bit of a fib, right? It's a bit of a colorful language that is trying to express in more down-to-earth terms what we've said here on the podcast several times, namely that what's really going on inside a proton is a set of quantum fields. It's not particles. It's just not particles. I actually discussed this in some detail in both the video version and the written version of Biggest Ideas Volume 2, Quanta and Fields, because it helps understand things about the Compton wavelength of particles. For those of you who know a little bit about this stuff, in particle physics, when you have a particle with certain mass, you can, by multiplying by appropriate factors of the speed of light and Planck's constant, you can convert mass into 1 over length, 1 over a distance, okay? And that distance is called the Compton wavelength of the particle. And so a lighter particle, a lower mass particle, has a larger Compton wavelength, and a higher mass particle has a shorter Compton wavelength. And if you think about the proton and say there are quarks inside the proton, forget about the sea of quark-antiquark pairs. Think about the 3 quarks, okay, that are supposed to be there inside the proton. If you look at the mass of the quarks, the mass is lower than the mass of the proton, okay? Therefore, the Compton wavelength of each quark is bigger than the Compton wavelength of the proton itself. How can that be? How can we fit a quark that has a larger Compton wavelength than the proton itself inside the proton? The answer is, the whole point of the Compton wavelength is not the size of the particle. There's no such thing as the size of a particle because there's no particles, right? There's waves in quantum fields, and this is a particular wavelength, and it's a wavelength at which something happens. The Compton wavelength is a particular kind of wavelength, namely, it is the smallest wavelength that the wave function of that particle can have, and still sensibly call it just one particle. Once you squeeze the wavelength of the particle to a smaller number than the Compton wavelength, what that means is it's a superposition of 1 particle and 2 particles and 3 particles and things like that. It's not just a single particle wave function, and the way that you can prove that is the energy is going to be bigger than what you would require to make more than 1 particle. So it's a sort of complicated quantum thing. So at the end of the day, there's just no such thing as the number of quark-antiquark pairs. If you were to somehow take a snapshot of an observation of a quark, of a proton rather, in some sense, you would see a bunch of quarks and a bunch of antiquarks. But if you took the same snapshot over and over again, you would not see the same number over and over again, and the details would depend a lot on the method by which you actually took that snapshot. Eric Coker says, how much has the popularity of Mindscape grown through the years? Oh, the answer is actually not that much. In fact, I think during the first year or two, we saw substantial growth, and then it's more or less leveled off. It might even have declined a little bit. I honestly have not been paying attention. Actually, so maybe it's grown. I have not been paying too close attention to this. The popularity of the Patreon support has grown slowly, I would say, but steadily. But the number of listeners overall, which is dominated by just the usual audio feed, is more or less steady. You get 50K listeners right away, and then some couple months later, you might have reached about 100K total listeners for a typical episode. It's interesting because podcasts are not viral in the same way that videos or social media posts or anything like that are viral, in large part because of the way in which people consume different media. If you're watching a video, or you're reading a post on social media, or you're even reading a blog post, you're looking at your computer while you are doing that, typically, or your tablet or phone or whatever, you're looking at a device. And it's very, very easy to see, while you're looking at your device, a link that will take you to another thing, right? So you can link from one video to another, from one social media post to another, and that's how things go viral. When you're listening to a podcast, you're very often not looking at your computer. You're driving, you're walking, you're working, whatever it is, and so there's no obvious way to click on something and go to another one. So in fact, I think the weird thing about podcasts is how bad the system for finding new podcasts is. It's shocking to me that no one has really tried to build a podcast sort of categorization and discovery system, you know? I mean, maybe the time has passed. Maybe podcasts have outlived their peak popularity, but there's not a lot of ways to get your podcast to be popular. If it's already popular, if it appears on, iTunes top list or whatever, then people will discover you. But I don't really know how people get their podcast discovered. I always, all the time, run into people who I would have thought would be Natural Mindscape listeners who never even knew there was such a podcast. The one exception, the one obvious way to advertise your podcast is to appear on other people's podcasts and mention it. I'm not very good at that. I get many, many more podcast invites than I'm able to say yes to, just the way other things to do. If Mindscape were my full-time job, I would be putting a lot more effort into making it popular than I actually am. The final thing worth saying is, of course, the internet is changing, and not in a good way overall, in the sense that it used to be that places like Facebook, Twitter, Yahoo, Google, their business was sending you via links out into interesting places of the internet. But increasingly, they decided their business is to keep you on their site. They don't want you to go to somewhere else. And so it doesn't really affect me very much, but the media, websites that are supposed to give you news and things like that have been absolutely killed by the fact that Google is not sending them links anymore, right? Twitter certainly isn't sending them links. Blue Sky has a tiny fraction of the total users of Twitter, or of X if you want to call it that. But the amount of traffic that is driven to websites is much bigger from Blue Sky than from X, because X doesn't want to show you links to other websites. So this is very, very counterproductive, and I think probably this also has something to do with podcast popularity, but I have no actual evidence for that one way or the other. Andrew Goldstein says, when you ponder a new or exciting hypothesis, or existing hypothesis, mathematical model or new fundamental law of nature, how much credence, if any, do you give to intuition, by which I mean feelings that guide a person without fully understanding why? I think that you should give a lot, because I think that's a feature, not a bug. I think that different people have different intuitions. I don't think of intuition, people are going to define the words differently. I don't think of it as spooky or unknowable. I think that you can grow your intuition over time. Near the end of the conversation with Jacob Berendis, when I asked him a question about what is my intuition for how the theory behaves in a certain circumstance, Jacob said, I just don't have intuition. That's not what I have. These theories are very far away from the real world. You have to sit down and do the calculation. I just don't think that that's right at all for me. But it probably is not a disagreement of substance. It's probably a disagreement of using the word. To me, what I mean by intuition in that case is knowing what the theory predicts without sitting down and doing the full calculation, right? If you learn in electromagnetism that if I take a charged particle and I shake it, it's going to give off electromagnetic radiation, okay? To learn that, you have to sit down and do the calculation, and one does that. One takes the class, or one is Professor Maxwell or whatever, and shows that this is true. But then once you know it, you get it. You're like, oh, okay, I can see why that's the case. You develop an intuition for it, and then you don't have to keep doing the calculation over and over again. When I talk about branches of the wave function splitting in many worlds because of incoherence, you can do the calculation and show that happens, but once you've done it, you know it, and then you understand what is going on. Now, Andrew's definition of intuition is feelings that guide a person without fully understanding why. I think that sometimes intuition is that. Sometimes you can have intuition and understand why you have it. But one way or the other, regardless of which definition you pick, I think that people, because of who they are, because of how they grew up, because of how they've been thinking, will put different emphases on different aspects of new ideas. How happy are you with indeterminism? How happy are you with non-locality? How happy are you with a theory that is not yet very well defined, but maybe could be fixed up, versus something that is perfectly well defined but ugly, right? And I think it's good that different people have very different intuitions about those things, because I want people working on different ideas to maximize our chance that as a community we will eventually find the right ones. Niles Dar says, do you think the constants of nature are truly fundamental, or might they someday be derived from deeper principles? It's always interesting to see, to me, when the universe seems to tilt in a certain direction. Well, I think it depends. I think that we don't know. It would be weird to say I have a strong feeling about this question. I'm someone who accepts that in our best understanding of the world, there are going to be certain facts that are simply there to be accepted rather than explained, but we don't know which facts they are ahead of time. So it's absolutely okay to try to explain constants of nature, like the mass of the electron or the fine structure constant or whatever. It's not okay to demand that there be a better explanation than what we have right now. They might have just been that way. So that's just life as a physicist, I guess. I'm happy to accept that. Kyle Stevens says, my friend is a self-described anarcho-communist. I feel it's an untenable position because there seem to be no viable paths to anarcho-communism, as centralized government and capitalism both seem like attractors of sorts. It seems that we would need to either abolish private ownership and travel through communism, or abolish the state and travel through anarcho-capitalism, both of which are strong attractors that would prevent us from reaching the end goal of anarcho-communism. Is my intuition correct here? Is this something you've thought about in writing your book on the physics of democracy? I think your intuition is correct. It is very much something I'm thinking about in the physics of democracy sphere. The idea of the stability of complex systems and basins of attraction for different configurations of complex systems is crucially important. And I think that you're absolutely right that, well, you sort of imply this, and I agree with it, that some people in their political or social theorizing imagine versions of an ideal society and argue that these societies would be ideal without putting enough effort into understanding the stability of those societies or social structures under perturbations. That is to say, do you really require for the success of your society that everyone behave exactly properly according to the rules of the society? Or if some people try to, if you live in an anarchy and some people start imposing rules on others that you're not supposed to, or if you live in a communism and some people start hoarding private property, is that a unstable mode? Is that something that can grow with time because people look at it and go, oh yeah, if that guy's doing it, I want to do it too, right? I think many features of ideal pictures of society have that problem. What I am not able to do is actually to calculate it, right? That's why I say I think you're right, but I'm not sure. I would love to know, a sort of disciplined framework in which you can say, here are the directions of instability for this particular social system or something like that. I mean, maybe someone has figured out that problem. I haven't actually come across it in my readings. John T. says, Sarah Walker asserts that according to assembly theory, nothing above a certain incredibly low level of complexity can just spontaneously pop into existence. This seems to contradict the idea that given enough time, every possible structure will form from random fluctuations. It also seems to suggest that there is a non-randomness to the universe, otherwise random fluctuation would be enough to create everything eventually. I think that this is just a matter of people being a little casual in how they're talking. I don't think that Sarah is saying that it is impossible given arbitrary amounts of time for complex structures to pop into existence. I think that what she's saying is, it is in the actual amount of time we have, sufficiently improbable that certain levels of complexity will spontaneously pop into existence that we can just ignore that possibility entirely. And that's 100% true. When we talk about things like Boltzmann brains or whatever, we always have to say this is something that becomes a worry when you have essentially infinity years to wait. The age of the universe so far, about 14 billion years, is nothing compared to the time scale that it would take to randomly fluctuate into a brain, even if you had a high density of matter and a large rate of fluctuations, okay? So those thought experiments for cosmologists are completely irrelevant for people who are trying to understand the origin of true complex systems in the actual universe. It's just a matter of being practical, not a matter of what is possible in principle. Scott Collins says, I get annoyed with people when I feel like they are just saying whatever pops into their head without giving it any thought, especially when they dig in afterwards. After listening to the episodes with Christoph Koch and Annika Harris and to her Lights On audiobook, I realized that we are basically all doing that all the time and then justifying it ex post facto. Certainly, thoughtful, carefully considered ideas are more than blurtations of the subconscious. How do you understand this difference in quality and value of expressed thoughts in this light? Yeah, I think you're right. I mean, I think that from what little I've read about how the brain works and how speech acts work and how people get through the day, a very large number, a frighteningly large fraction of our words that we say or sentences that we say out loud are not really arrived at through careful, deliberative, logical thought, okay? And maybe it would be entirely impractical to do that. There's the old distinction between System 1 and System 2 that was popularized by Daniel Kahneman in his book Thinking Fast and Slow, and I always forget which one it is. One is unconscious thinking, I think that's System 1, and then System 2 is the sort of conscious, slow, careful thought. So System 1 is fast, System 2 is slow, and the idea that almost all the thought is System 1, actually, and System 2 sort of goes along for the ride, occasionally butting in. But there's a reason for that. The reason is that you don't have time. You don't have the energy, literally, in your brain. You don't have the resources to do all of your thinking at the level of careful, logical cognition. it turns out that we get along like that anyway, right? Like, we're not, if you had to justify everything you did while driving a car every time that you tap the brakes or the accelerator or turn the steering wheel or whatever, it would be a disaster. You have to just sort of act subconsciously a little bit. That's why it's hard to learn at first, then you get very good at it. And I think that what happens is you should try to get good at speaking and talking and conversing in the same way. That is to say, you should set up your unconscious thoughts, which can be effective, right? Like, they're not, completely beyond our control. You can train them a little bit. We should train them to be good unconscious thoughts. We should train them to be unconscious thoughts, or subconscious thoughts, I suppose I should say, that we are not embarrassed to let out there into the world. And we can do that training by constantly trying to think carefully, by reading and conversing with people who are good thinkers themselves, and otherwise, marinating in good thinking rather than bad thinking. Part of the reason why we're here at Mindscape talking to smart people. John Campbell says, what makes energy so special? Lagrangians have lots of symmetries, but energy seems to be the most important for understanding systems. What gives? Well, remember just a few minutes ago, when we were talking about continuity through time, right? The laws of physics say that systems they're not exactly the same from moment to moment in time, but they do persist and change relatively gradually and smoothly through time rather than dramatically. And remember that Emmy Noether proved long ago that there's a relationship between symmetries of nature and the existence of conserved quantities like energy. What symmetry is related to energy? The answer is time translation invariance, changing from moment to moment in time. What makes energy special is that it is the conserved quantity that is sort of related to, or even you could say in charge of, evolution through time. And evolution through time is crucially important to us here trying to understand the world. In quantum mechanics, it's the most literal, well, let's say in the Schrödinger equation, it's the most literal relationship you could imagine. The Schrödinger equation says that the rate of change of the quantum state is given by acting the Hamiltonian on the quantum state, and the Hamiltonian is literally the things that measures the energy of the system. The time derivative is not given by acting the momentum on the system. That's a different thing. That's something that you can do, but it's not quite as central and fundamental as the Hamiltonian is, so that's why everything seems important. Dale Addison says, if you had kids, would you tell them that Santa Claus is real or be honest from the start? Sam Harris has argued that parents shouldn't lie about Santa since the potential sense of betrayal and loss of trust isn't worth the added excitement. He sees it as a small but meaningful deception, one that promotes magical thinking over critical thinking and may undermine a child's relationship with truth, reason, and trust. I don't really think it's a big deal. I don't care that much one way or the other. I truly don't think it's a big deal. If parents want to tell their kids that Santa Claus is not real and be perfectly honest with them and try to admonish them to, at least take their friends' feelings into consideration when they talk with their friends, that's fine. If parents want to tell the story of Santa Claus and act as if it's real and only reveal the entire truth later, that is also fine. Stories are okay. Stories are part of life. Coming to realize that certain stories were simply entertaining and not literally true, that's also part of life. It would be important if the telling people a story about Santa and then only later removing it and explaining that it was just a story did actually undermine a child's relations with truth, okay? If that were true, it would be important. I would take that into consideration. I would like to see data about this. Has anyone actually done a study that shows that telling people that Santa delivers presents makes them less likely to be critical thinkers later in their lives? If that's true, then I would move to the side of not telling people about Santa, but until I see that data, I'm a little skeptical that that's actually a strong relationship. There's many other things going on in the real world. Ted Ferris asks a priority question. Everett's many worlds interpretation assumes a deterministic universe. The universe we see is a probabilistic one where the uncertainty principle prevents us from knowing the path of an electron, although we can predict how a probabilistic distribution will fall into a range of outcomes. If the assumption you make in your argument for many worlds is the universe is deterministic is wrong, and the universe is in fact probabilistic as it appears to be, would you give up on the many worlds hypothesis? And what is your basis for assuming the universe is deterministic? So I don't quite think that's how it works. The phrase, what is your basis for assuming the universe is deterministic? I don't start by assuming the universe is deterministic. You start by contemplating the theory that you're faced with. One theory is Everett, one theory is Bohm, one theory is spontaneous collapse, etc., etc. Different theories have different aspects to them. Everett is a deterministic theory. Spontaneous collapse theories are not deterministic. I don't care whether the universe is deterministic or not. I don't start by assuming it's deterministic and then look for a theory that satisfies that. I look at Everett and say, oh, it's a really simple theory that explains the data. That's it. If we find that the real world is not deterministic, even at the fundamental level, not just at the apparent level, because obviously in Everett, as in every version of quantum mechanics, the world we observe, the world we experience is not deterministic. The Everettian explanation for that is you don't experience the whole world. The whole world is deterministic. If somehow we got, I don't know, a message from advanced aliens saying the fundamental laws of physics are not deterministic, then I'd be very happy to give up on Everettian quantum mechanics. That would be a falsification of that idea. Jeremy Dittman says, how is the quantum mechanics textbook going? Specifically, you mentioned in your episode with David Tong that you are opting to introduce quantum mechanics both from the Schrödinger equation point of view and the qubit approach. And I'm curious if you can get into spin right away for whichever 2D Hilbert space example you've chosen to dig into. As an undergrad physics student, I remember how difficult the concept of spin was, since it couldn't be thought of in terms of macroscopic spin concepts, but still mysteriously share the same symmetries, vector properties, etc. as classical angular momentum. Just wondering if you have developed an intuitive approach to spin, or if it's one of those things that is tough about learning quantum mechanics. I'm sort of not there yet in the writing of the quantum textbook, to be honest, but I will say this. I do qubits, but I don't sweat too much spin as an idea early in the book. Spin comes later in the book. There is a textbook that has been used at Johns Hopkins previously by John Townsend, which is a very, very good quantum mechanics textbook. The reason why I don't want to use it is because it is a qubit-first approach, and because of that, he spends a huge amount of time relatively early in the book dealing with details of angular momentum. I think that the ordinary, everyday, non-relativistic Schrödinger equation does not appear in his book until page 214 or something like that. I looked it up. And I think that's doing a disservice to the students. There's a thing that it's possible to be too logical in your presentation, right? Because the students are not empty vessels into which you are pouring your knowledge. They have pre-existing knowledge of some things. One of the two things they have pre-existing knowledge of is classical mechanics. And to just present quantum mechanics as magical and new without connecting it to classical mechanics is hard. And I think that starting with classical mechanics and then explaining how it becomes quantum mechanics is helpful, and that means wave functions of particles moving in a continuum rather than discrete qubits or whatever. Now, as a matter of empirical fact, the simplest... let me back up and try to make some sense for people who are not quantum mechanics experts. In quantum mechanics, quantum states are vectors in Hilbert space. Different physical systems have Hilbert spaces of different dimensionalities. A single particle moving in any number of dimensions corresponds to an infinite dimensional Hilbert space, and there are a lot of mathematical subtleties that get in the way of teaching that. You can think of finite dimensional Hilbert spaces, and what is called a qubit is a two-dimensional Hilbert space, or a vector in a two-dimensional Hilbert space, and you can talk about Hamiltonians and interactions and all that stuff. And then you can say, what kind of physical system is represented by a qubit? It turns out that lots of physical systems are represented by qubits, and that's why building quantum computers is something where there's a lot of different experimental, technological, engineering approaches that are being used. But the most direct one is the spin of a spin 1/2 particle. The spin of a spin 1/2 particle is either up or down. Those are the observational outcomes with respect to some given axis along which you're measuring the spin, so that's a qubit right there. So it is very natural, if you want to talk about qubits, to say, okay, what is a qubit? What's an example? Oh, a spinning particle. Oh, what is spin? And then you get into angular momentum, et cetera, et cetera, et cetera. But they're conceptually different things. The idea of a qubit is not necessarily tied to the idea of spin, okay? So you can use qubits as just a abstract way of talking about Hilbert spaces and different formal structures in quantum mechanics, tensor products, entanglement density matrices, things like that. That's what I want to do. Talking about spin and angular momentum is super important in quantum mechanics, but it's a little bit separate from that, and for me it will go later in the book. I do think, to be honest, that many discussions of quantum mechanics in textbooks overemphasize the idea that spin is not the same as ordinary angular momentum. It kind of is the same as ordinary angular momentum. What is not true is that the electron is a little ball with a fixed size that is literally spinning. That's not true. But spin is angular momentum, and it should be treated kind of the same way. It's a subtle distinction, but I think it's a crucial one. Emerge Holographic says, the other day I saw a video of Richard Dawkins and Lawrence Krauss comparing gender identity to healthy obesity as concepts nobody should entertain. I am transgender and fact. Both of their work, Krauss and Dawkins, inspired me at points in my life, so needless to say, it's frustrating to see influential scientists harming people who they don't understand due to misplaced atheistic authority. We often see this happen disproportionately with marginalized groups, especially indigenous practices. As you are someone who can see the world from multiple emergent levels, what do you think it is that empowers brilliant minds to reductively redefine and dismiss the human conditions of strangers? Well, there's a lot going on here. I feel sorry that you have to go through this. You know, my apologies for that on behalf of the wider scientific community, etc. It's very frustrating. I get that. The first thing that comes to mind when you ask a question like this is my repeated exhortation that you should never have heroes. Having heroes is a bad thing. It's not because individual people are not good and admirable and worth looking up to, but it's just very often the case in the idea, in the conception of what it means to be a hero, that someone is really, really good at something, whether it's science or communication or athletics or music or acting or whatever, or politics, and we think, oh, that's a good person, that's someone I admire. And then we find out, ooh, they're very bad at other things. And that's why you shouldn't have had heroes in the first place. You should admire people for doing what they do well, but not imagine that goodness transfers over to different aspects of who they are in their lives. If you're going to have heroes at all, have heroes among the set of people who you know personally and who you can vouch are really actually good people, right? They behave in good ways in a variety of different circumstances. Those are the heroes that you have, not famous people, right? When it comes specifically to scientists and atheists in particular, I'm someone who does absolutely think that the moment in history of new atheism being a big deal was overall good. I think that it was important to emphasize to people that it's okay to not believe in the existence of God, to give a permission structure to people who don't want to go to church and things like that, to give atheism a seat at the table of reasonable people, and I think the New Atheist movement did that. I also think that, as a matter of fact, it had a lot of bad aspects to it. And I'm just going to single out one part. Among you can have a long conversation about this. One part is a sort of reductive over simplicity about thinking about the world. This is sometimes called engineer's disease, but it's also physicist's disease just as much. Namely, the insistence that I don't need to think very hard. Or I don't need to keep lots of different subtleties in my head. The world is basically black and white. It's pretty simple. As long as I figure out what the right aspects of it are, I can actually figure things out without too much work. And this attitude goes hand in hand, especially in the New Atheist movement, with an idea that people who think this way are the rational ones, right? You will very often find a certain set of people who think that what they do is simply thinking rationally, and other people don't think rationally. And ironically, one of the things that, as a matter of evidential fact, tends to be correlated with calling yourself rational is a difficulty in seeing when you're not being rational. Because you latch on to that simplistic explanation, and you kind of close your eyes and ears to the evidence that doesn't go along with it, because you're too busy congratulating yourself on being rational. And so I see a bunch of people who are smart people by any conventional way of calling themselves smart, who just don't want to be bothered with the complexities of life. And the one more aspect that matters a lot here, and this is true for a bunch of atheists, but also a bunch of non-atheists, people don't like to think that they personally are anything other than perfectly moral and good. One of the things about thinking about marginalized groups, indigenous practices, or even just kinds of people who you personally are not very familiar with, is that you can very easily think about them in wrong ways. You can very easily stereotype them. You can very easily hurt them, even without meaning to. And that's fine, that's just human. The question is, when you're told that you're doing that, do you face up to it and try to do better, or do you double down and say, oh, I'm not a bad person here, I'm very good, you clearly are, whatever it is, you make some excuse for why people think that you are acting badly. You see it in many, many different ways. I think, a very classic example is the use of pronouns to discuss people, right? There was a movement, to say, look, there's examples of people who don't fit into the most common gender dichotomy of he and she. Maybe they want to be called the other pronoun than you might guess on the basis of their presentation or their earlier history, or maybe they don't want to be using he and she pronouns at all. They want to use they, them, or whatever. This is a very, very tiny ask in my mind. How hard is it to call people what they want to be called, especially if the words you're being asked to use are already words you use for other purposes to call other people anyway, right? But it engenders an enormous backlash way out of proportion to what is being asked. Why is that? Because you're pointing out to people that maybe they've been acting in a way which isn't as moral and upstanding as they thought. Maybe they're acting in a way by calling people by pronouns they don't want to be called by, or by names they don't want to be called by, or whatever, that hurts them. Maybe you didn't want to hurt them. Maybe you're all well-intentioned, but maybe you are doing it. Certain kinds of people will hear that and go, maybe you're right. Let me think about that. You might be right. Maybe I should change how I behave. Other kinds of people are just going to be outraged by the suggestion that they were misbehaving in any way. You can come up with your own examples. I'm not going to start listing lots of examples. Racism is, even more obvious of an example where people don't think that they're racist, but they become more and more obnoxious the more you point out to them, well, maybe this particular behavior you're doing is a teensy bit racist, and maybe you could be better at that, right? People don't want to be told that. And to be super duper honest, there's another set of people who take absolute delight in telling people that they are racist or sexist or transphobic, and they feel a certain amount of righteousness in making these accusations, and those people are annoying too. It's kind of hard to balance the complexities of the world. In a slightly different vein, and I realize I'm going on here about this, I didn't realize I had that much to say about this, but in a slightly different vein, recently on Blue Sky, there was a lot of discussion about the manosphere, right? That is to say, the groups of influencers who are speaking to young men and telling them that, they should behave in certain ways, the world is against them, etc. Or for that matter, Trump voters, right, who are convinced that they are not being respected by society and things like that. All of this is because, to vastly oversimplify, and the irony here is I'm vastly oversimplifying by accusing other people of vastly oversimplifying. So, okay, fair enough. I'm going to do it anyway. People, life is hard. Getting through day-to-day human interactions in society is tricky, right? We make mistakes. All of us have said things that we regret. We have spoken awkwardly. We've been embarrassed. This is just 100% human. And because of that, there's a certain cast of mind that says, I wish everything were simple. I wish there were rules, right? This is a big part of the attraction of a desire to go back to some version of society where everybody's role was very, very explicitly laid out. You have to wonder less about what is appropriate behavior if you're told by society this is appropriate behavior. In a world where you might have to actually adjust your ideas of what appropriate behavior is from time to time, from context to context, from person to person, that just makes all of the anxieties that you had about living in the world more obvious and in your face and worrisome. So nevertheless, you got to do it. Too bad. Living in the world isn't always easy. There's not always a set of simple rules, and the rules that do exist aren't always the ones that you were taught when you were a teenager. Sorry about that. I think that the good people, the people who are oriented toward caring about the lives and feelings of others, will put in the work to try to change their behavior into something that everyone can be happier about. And I hope that we all do our best to do that. JMS547 says, I really enjoyed your episode with David Tong. In it, he mentioned solitons in quantum field theory. He described solitons as topological structures and drew the analogy with smoke rings. As no stranger to quantum field theory yourself, you might be able to answer, does this conception of a soliton have anything to do with solitons in integrable systems, e.g., and this is a bunch for those of you who don't know, but here's a bunch of integrable systems that have solitons. The KdV equation, nonlinear Schrodinger equation, total lattice, etc., lax pairs, inverse scattering transforms, nonlinear Fourier spectra. Are all those involved? And if so, are techniques from integrable systems used in quantum field theory? Yeah, absolutely, 100%. Those are all very, very tied up in how we think about solitons in quantum field theory. The kinds of solitons that I personally have thought about at a relatively deep level are the topological defects that you get in some quantum field theories. These include monopoles, cosmic strings, domain walls. I've written a few papers on those kinds of things. There, the fundamental focus is on topology, which I knew something about. I had the relevant math courses. I could calculate a homotopy group when necessary. So that is the part I understand. And there you don't need to worry too much about details of differential equations. That's the beauty of topology. The topological perspective says that under certain circumstances, there's going to be a soliton there because topologically there's no way to get rid of it, right? Like if there's a knot in a piece of string and you fix the ends of the string, that no way you can move the string around is going to remove the knot, okay? It's as simple as that, without knowing details of how the string moves. Other things like the KdV equation, etc., might involve actually caring about the differential equations, at least until you understand it well enough that you reduce it to some topology problem. But anyway, yes, I think that all of these ideas are very closely connected. There's a lot of work on these in the context of QFT. Eric says, in the March 2024 solo episode, The Coming Transition in How Humanity Lives, you made a compelling point. As price, efficiency, and economies of scale increase, consumers often become less happy and feel less able to influence large institutions. Do you think this growing sense of powerlessness is a key reason why so many people today feel like things are worse than they used to be, even if, on paper, life is improved in many ways? Is this loss of agency an unavoidable side effect of a system optimization? Or are there ways to reconcile the individual's well-being with the efficiency of the broader system? Is this an inevitable consequence of capitalist democracy? I don't know. I see well, so let's put it this way. Maybe it could very well be. I think that one could, I've not seen this argument be made, but I can imagine making an argument that says that improved technology and also surveillance, right, improved knowledge of the audience, of the populace and their interests. We all know that's happening, right? We all know that corporations know more and more about us and what we care about than they ever did before. And that can be used to squeeze a few more pennies out of people. I don't know if it's inevitable. Inevitable is a very strong word, but I do think it's sort of natural to expect that the cost of doing business in a million different ways will be driven right to the point where we can barely tolerate it, right? And that was part of my point in that solo episode. Of course, as we just discussed before, you don't have to live at the whims of the free market, right? You could pass laws preventing this from happening. And I think that under egregious examples, that's probably what's going to happen. But a lot of examples are less egregious than that, right? They're sort of sneaky. Like apparently some companies are just bragging about it and they're getting themselves into trouble, but others are going to do it anyway without bragging about it, and they're going to make themselves a lot of money and make the rest of us unhappy. So maybe, yeah, I don't see why it wouldn't be, but I'm a little bit not quite confident enough to say that it's inevitable. Richard Graff says, I enjoyed your recent solo episode on complexity. In it, you discussed how complexity arises from systems that are highly, but not, I assume, not completely ordered. My question is, can a system be completely 100% ordered? And if so, can complexity arise from such a system? Well, there's something specific that I had in mind when I was talking about the evolution of complexity, which is that the underlying laws of physics are the ones we know, okay? So the ones we know, as we discussed earlier in the AMA, have the property that information is conserved over time, that you can run the system forward and backward from a starting point. If that's the case, then if you start in a completely ordered state, typically you will just stay in a completely ordered state. You could probably reverse engineer some weird rules that would allow complexity to arise. There's no theorem that says it couldn't happen. You can start in an ordered state and then move things around to get to a complex state in a completely information-preserving way, but that's not typically what you would actually get. If you start completely ordered, you stay completely ordered. As opposed to ideas like Stephen Wolfram has explored, where you have irreversible laws of physics that do not conserve information, and then you can start in a very, very simple, completely ordered starting point and get complexity coming out. So the answer, I think, depends on what you think the fundamental laws of physics are, and we don't know that exactly yet. Yazan al-Hajari says, as an artist drawn to Gödel's incompleteness theorems, I wonder what they tell us about the ultimate limits of human knowledge and consciousness. Do you see any natural connections between Gödel's work and the puzzles of quantum theory, or even with the idea of perfection and unavoidable contradictions in a hypothetical perfect being? No, I don't really see those connections there. Roger Penrose has drawn some connections, not, his connection between Gödel and quantum theory is quite indirect. But he draws a connection between Gödel and human thinking, and then he uses quantum theory as a way to help explain how human thinking can maybe overcome the limitations of Gödel's theorem. I think that, like most people who are experts in this area, I think that that argument doesn't quite fit together. Quantum theory is actually the opposite of what is happening with Gödel's theorem. Quantum theory, at its heart, is super simple. It's a single equation, the Schrödinger equation, with linear evolution. There's not even the nonlinearities and chaos that you would get in a lot of classical systems. There's apparent complexity for reasons I discussed in the complexity episode. Once you have branching and wave functions, you can have a simple overall quantum system that is a superposition of many individually complex branches of the wave function. But other than that, quantum theory is not really a puzzle that you need to resolve using ideas like Gödel's theorem or incompleteness or anything like that. As far as hypothetical perfect beings are concerned, I would argue even more directly that the idea of a perfect being is simply incoherent. What does it mean for a being to be perfect? I understand what it means for a circle to be perfect or imperfect. I don't know what it means for a being to be perfect. You haven't given me any quantity that I can maximize, right? People just use phrases like that in ordinary English language to gesture toward some notion of greatness that they haven't really sat down and realized doesn't quite hang together as something sensible. Rizard Sommerfeld says, I have aphantasia, the inability to voluntarily create mental images of things I'm thinking about. Do you think that inability could be an advantage when it comes to thinking about and understanding physics by forcing the mind to map and understand concepts without any innate imaginary visual substrate to build on? Or do you think that ability is fundamental to understand physics deeply? That's a good question. I wouldn't guess that it would be an advantage to port or, in any different kinds of circumstances. It might be that there are places or conditions under which that's an advantage. I mean, it is very well known. It's most clear in mathematics rather than physics, but mathematicians are either algebraists, algebraers or geometers, okay? So they think in terms of equations, like in algebra, or they think in terms of pictures and figures, like in geometry. It's kind of the math version of left brain, right brain, right? And physicists are likewise. Some physicists rely very heavily on visualization in their work, others do not. So I think it's not a matter of, like as we were talking about before in the neurodivergence discussion, it's not a matter of advantage, it's a matter of difference. And difference and diversity are useful because we don't know ahead of time the best way to get from point A to point B, where point A is where we are in our current understanding of physics, and point B is some better understanding. So I wouldn't say whether it's an advantage or not, but it's a feature that would help, train your intuition about doing physics, and that might lead you to insights that someone else doesn't get to as quickly as you do. It might also prevent you from getting insights that someone else does get. That's okay. Different people are different. That's what makes the world go round. Neil Wallace says, I'm a creative person, a graphic designer by trade. I naturally picture things, scientific models particularly, in a visual way, sometimes abstract yet still imaginable to me. However, it seems I have no way to visualize the infinity of our universe. As a scientist, do you use any pictorial methods to consider this most beautiful of enigmas? So this connects a little bit to the previous question, but is different enough I didn't want to group them together. And I've said this before, visualization is something that is very, very helpful in certain circumstances in doing physics or math or science or whatever, but it is not a requirement. It can't be a requirement. There are things that you can't visualize. You can sort of kind of try to visualize four-dimensional things. You can't even try to visualize 10 to the 120 dimensional things. That's just not a thing you're going to be able to visualize, right? You can visualize a three-dimensional thing, kind of, and then, imagine the properties of that thing carry over to the more abstract case. But at some point, you're going to have to write down equations and trust what they tell you, and that's okay. You're allowed to do that. Infinity is absolutely... Is it visualizable? Well, yes and no. I cannot visualize the integers, personally. You can visualize a little bit of them. When I say the integers, what do I say? I say the numbers 0, 1, 2, 3, 4, ... and -1, -2, -3, -4, ... The ... dots are covering a lot of sins, right? They're covering a lot of an infinite number of extra numbers that I do not have time or space to list. Am I truly visualizing them? No. But can I work with them? Yes. If I have... it wouldn't be that hard for us to sit here right now and state an integer that no one else has ever stated in the history of the universe, right? Take the first 5 million digits of pi, okay? Write them to the left of the decimal point as an integer, and raise that to the power 381. There you go. I made up an integer. That number is so big that no one has ever mentioned it before. But I could tell you, what would happen if I added 1 to it, right? I could write down that number. I could figure out whether it's even or odd, things like that. I could manipulate it with the rules of arithmetic, even though no one has ever written it down or thought of it before. That's how science works, and you don't necessarily get to demand that you're able to visualize. Having said that, I visualize all the time. I'm closer to a geometer than an algebraist, but I just visualize little toy things, right? I visualize -4, -3, -2, -1, 0, 1, 2, 3, 4 with the ... dots. And on the basis of that, I can talk about the integers. I can visualize a little three-dimensional Hilbert space. And on the basis of that, I can talk about 10 to the 10 to the 120 dimensional Hilbert space. But you don't rely on that visualization. It's not the honest representation of what's going on. Stephen Bryant says, it is thought that when life began on Earth, conditions were very different. No free oxygen, for example. Suppose there were a large, isolated, lifeless system with today's conditions. Is there any reason to think that life could arise spontaneously, or any reason to think that it couldn't? I don't think there's any strong reasons one way or the other, to be perfectly honest. We had Nick Lane on the program. We had lots of people talking about the origin of life, but Nick in particular is part of a group of people who have a view on the origin of life, the metabolism first view, that has specific ideas of how life might have formed. One of them is Michael Russell, who I've quoted many, many times. He's another metabolism first person. And in the 80s and 90s, he used his ideas about how life formed to argue that there must be, on the bottom of the ocean, right, on the surface of the ocean floor, a particular kind of hydrothermal vent that no one had ever seen before. A warm alkaline hydrothermal vent, as opposed to these acidic hydrothermal vents that had already been discovered. And after he made the prediction, they found it. The Lost City Formation, you can go and Google it, was found by Alvin. Remember Alvin, a little submersible that looked on the bottom of the Atlantic Ocean for all sorts of interesting things? So there it is right there. It is an existing warm alkaline hydrothermal vent. Life could form in something like that, as far as we know right now. So there's nothing that we know about either the origin of life or the Earth's conditions today that rule out the possibility that life could arise spontaneously. It might have spontaneously. it might have been the case the conditions in the early Earth made it easier for life to form. That I'd be perfectly open to. But I don't think there's a deal breaker for life forming now. Tim Converse says, I get it that there must be some facts that are brute. Otherwise, there would be an infinite regress of explanation. But I find myself uneasy with the idea of genuinely brute facts that both seem complicated and arbitrary. Like there are exactly x different things at type T, where x is a small integer that is not as small as 2 or 3. As an example, suppose that some version of string theory were true and it required there to be exactly 11 spatial dimensions, no more, no less. By the way, pause. It's 11 space-time dimensions that you get in string theory, typically, so let's imagine that we're talking about space-time. Why 11? Tim continues. That's just the way it is. I would crave some further explanation, even if it's a landscape multiverse style. B could have other values, but in our universe B equals 11. The universe doesn't have to respect my feelings of uneasiness, but with regard to our own credences, does this kind of seeming arbitrariness of a fact reduce your credence that it could ultimately be a brute fact? It does, but only a little bit, I would say. You know, I'm a big believer that we don't get to choose what the brute facts are. It's interesting that you choose the idea of 11 dimensions, because I don't know whether this is where you got it from, but supergravity, which is a close relative of string theory, but not the same, is a theory that does naturally live in 11-dimensional spacetime. String theory naturally lives in 10-dimensional spacetime. Supergravity naturally lives in 11 dimensions, and they're related to each other. This was the big mid-1990s discoveries of people like Joe Polchinski and Ed Witten and others relating all the different string theories and supergravity to each other. And 11 does seem like kind of an awkward number, right? I mean, 2 or 3 is easier. 11 seems weird, but it's not arbitrary in any sense. You know, it comes from thinking carefully about what supergravity is, supersymmetric gravity, thinking carefully about how the more supergravity you have, the more supersymmetry you have, the more spins, types of spinning fields are related to each other, and the fact that if you have spins greater than 2, then things seem to break down and give you inconsistencies, and you find that 11 is the dimension of where you can have the largest amount of supersymmetry that you're allowed to have, right? So it's a calculation that leads you to 11 dimensions. It's not that it's just some arbitrary thing. Likewise, the 10-dimensionality of string theory comes out of saying we want to be able to quantize propagating strings in a way that is stable and free of anomalies, and it turns out from a long complicated calculation, it can only work in 10 dimensions, at least in perturbation theory. So that's one of the reasons why you shouldn't be too precious about saying this or that number just seems arbitrary to me. I don't know where it came from. Maybe it comes from a calculation that you just don't know how to do yet. The bigger problem is something like, what if the Hilbert space of the universe is 10 to the 10 to the 122 dimensional? That's a number that seems kind of awkward. Where did that come from? I really don't know, but maybe it's a brute fact. Maybe we just have to live with it. Mikhail Brzezinski says, even when we finally transition to renewable energy, we will have warmed the planet by at least a couple degrees. What are our hopes of reversing this within the next 50 years by sucking out the excess carbon or other climate engineering methods? Is any such technology on the horizon? I don't know, 50 years is the toughest time scale, because like if you're talking about 100 or 1,000 years, then I have no idea what's happening. If you're talking about 10 years, then we have a reasonable idea of what might be possible. 50 years is right there on the boundary. It's absolutely conceivable, given what we know about engineering and chemistry and physics, that we could change the atmosphere of the Earth. By far the easiest thing to do is just to make the atmosphere of the Earth a little less transparent. Right? To put up some particles in the upper atmosphere that reflect a little bit of the light from the sun. That's much easier than removing excess carbon from the atmosphere. It's something that you could do, that you could certainly imagine doing on the 50-year timescale. The question is, how sure are you that you really understand the unanticipated consequences of doing that? You might, what if you go too far? What if you make it 2 degrees colder than it is right now? That might be just as bad. What if there's some toxic effects that arise from doing that in unanticipated ways, and you just spread some poison in the atmosphere of the whole Earth? What if the natural motion of the wind currents of the Earth mean that it all concentrates over the United States? The rest of the world keeps heating up and the United States is plunged into an ice age, right? Well, I don't know. These are all possibilities you would have to consider. Taking the carbon out would be more direct and more predictable, but it's harder to do. So I think that, we have to do both strategies of cutting down on our use of fossil fuels and thinking about ways to engineer fixing the atmosphere. As I mentioned at some point on another episode, some people don't want to hear about attempts to fix the atmosphere, to engineer a reversal of global climate change, because they think talking about that lowers people's incentives for cutting down on fossil fuel and greenhouse gas production. I don't think that's right. I think we have to act like we're grown-ups and we can think two things in our head at the same time and do everything we can to solve the problem. The problem is just that big. Okay, the last question for today's AMA comes from Gary Miller, who says, I've listened to countless hours of your podcast, and it's always been a one-way conversation. You are speaking and I am listening. One time I met you at a book signing in LA. You kindly signed my book, and then you asked if I was a physics fan. I was dumbfounded in all of our conversations. I was never expected to respond, and suddenly I was tongue-tied. Are there people, scientists, authors, celebrities, who you've met and suddenly found yourself a bit off your game or at a loss for words? You know, I'm going to try to be as honest as I can about this. That's a very sweet story. Thank you for telling it. These days, not really. Like when I meet famous people, which I sometimes do, I'm not generally very tongue-tied. And I think that's in part because I've been around long enough and gotten to meet enough celebrities that celebrities in a very broad sense, like including famous scientists or politicians or whatever, that you very definitely learn that they're just people. They're nothing special about celebrities, right? They have all the good qualities, all the bad qualities that other human beings have. I've met a large number of Nobel Prize winners, famous actors and musicians. I briefly had a chat with Barack Obama when he was running for the Senate back in Illinois. So he wasn't as famous as he is now, but he's super charismatic right off the bat. And you're like, oh yeah, this guy's going to be president someday, very clearly. But it's happened enough that I don't really get tongue-tied. Back in the day, when I was younger, I absolutely would. I would absolutely be intimidated by meeting certain people, let's put it that way. I can't quite remember a specific incident where I became tongue-tied and couldn't say anything particularly witty or insightful. What I remember actually is the opposite of that. Sometimes you might have heard me on the podcast talk about Alinea, which is my favorite restaurant in the world, which is in Chicago. It's a fancy molecular gastronomy restaurant that you go to on a special occasion. And one time I went with a couple friends of mine, and we had this beautiful meal, and it was still relatively new in the existence of the restaurant, and so they were still trying to build a reputation and everything. And we got the chance to go back to the kitchen and talk to Grant Achatz, who is the head chef. And he's a very interesting guy. I encourage you to go look him up and listen to his interviews. But my friends did the opposite of the tongue-tied thing. They kept talking about the meal. They kept telling him, and he didn't get to say anything. I didn't get to hear anything that Grant Achatz had to say. I would have liked to hear something. I would have liked to ask him a question and let him talk. But, people react to these slightly nervous situations slightly differently. Some get tongue-tied. Some get a little bit, they go on for many, for however long they can keep talking, and that can be a very long time. So people react to different experiences with famous people or big names in different ways. Don't, is my advice. They're just people. But by the way, the flip side of that is also true. Famous people are just people, which means sometimes they might be in a bad mood for reasons that have nothing to do with you, right? They might have gotten some bad news. They might just be tired and cranky. Don't feel bad if you meet a well-known person, a famous person, and they're not very personable or voluble or immediately warm and welcoming. I've certainly met famous people and tried to talk to them and basically gotten the brush off. I don't blame them. This is a feature of being famous. Really famous people, not like me famous, but really famous people, you can't walk around, right, without being bugged all the time. And some people like it. Some people don't react well. Some people maybe like it some of the time, and other times just are not in the mood. They're all human beings with all the pros and cons of that, as we all are. Our commonalities are more than our differences. And with that super profound thought, thanks as always for supporting the Mindscape podcast. I hope you enjoyed this AMA. I will talk to you next month.
A clan is just a family you choose to join. Did the bird distract you? He does that. Are you judging me for selling out and moving back to the city? You are judging me. Birds.
but me still not hear them. Them coulda never pay me fi fear them. Me make reggae and say having a party is a punky reggae party. That mean punk reggae. I make a song right.
Hey, what's up? If you ever trying to steal some money from some sucker-ass fool and don't want to get too close to him, holla at your boy LD. I'll send one of the homies to go through there and get with him.
I was just thinking, what is, like, the most important thing? Privacy, right? Like, I can buy a butt plug online and no one has to know. And if you can do it for dildos, we should do it for acid. That's our next move. Just go to the drop points and hide the packages for the clients. They'll pick it up from there. weren't too fucked up to send us the money. Good work.
All right, we might be ready to move on this thing. If you want to work, you'll get a knock on your door any minute.
Hey, y'all.
How you doing? Peace. Don't know what you're doing hanging around, and we got a hustle on? Hey, what's... You showed up on that last job. Lot more cash where that come from if you keep it up. I ain't bye. How's that job coming? Peace.
Yeah, you ain't ready for this.
Motherfucker!
Better move it before I come over the top.
Well, I guess I am officially out of retirement. Let's get this arcade up and running and get to robbing us a casino, huh? The staff's already on board. Meet us there, and we'll see what needs doing.
Come on, bud. You're missing out here. You need some BST.
When my Uncle Les said that this job was in games, I was thinking more of a esports league, you know, like packed out stadiums and global streaming rights and professional athletes that make millions of dollars, and they look like me, not a museum. I mean, some of these games are older than I am.
Okay, do you want the gig or not? There's a bunch of kids who chopped their arms off, but the boss told me I had to give it to you.
No, I do. I want it. Just tell me what to do.
Do you know how to use a broom?
Wendy!
Hey.
Hey, how's he doing? Actually, don't tell me. Jimmy, Everyone has to start somewhere.
I know. This is not how privilege is supposed to work.
He's a family friend. I give him a week tops. Oh, so, what do you think? We need some more cabinets, a bit of a spruce up. This way. You know, I grew up in these kinds of places. Figure I might as well grow old in one. And this laptop will tell you everything you need to do. Why don't we, hear our fortune,
The odds are in your favor when you cheat.
Little something I put together. Anyway, of course, we'll have to get set up down here, too. You gotta use your imagination. Now, this is an area for your crew to work.
Richmond.
We'll get some food and discuss it all.
Sure thing. I'll, it's a date. An appointment.
You're so funny. Good work. This place will be perfect. Let's go.
Okay, I'll come back once you've got everything set up. Call me, okay?
Welcome to my app. Yeah, I wrote it. No, it's not a big deal. Eventually, you'll use it to manage the arcade and purchase all the classic cabinets we're definitely gonna get, right? But at the moment, it's locked to essential purchases for the setup. Some basic equipment and a few of the Street Crimes GWE cabinets. Click on the link when you're ready to roll. Okay, we're rolling. We're gonna turn that wreck into an arcade and a heist HQ. So, you gotta collect some game cabinets and planning equipment. It's all paid for and waiting on the back of a flatbed. Pick it up and bring it in.
I'm on the clock. What you want? Some wheels? I'll get there as soon as I can.
Georgina gave us a little seed money to get us going. Ain't it nice having a rich benefactor who wants nothing out of this deal except seeing the money men suffer? From what I hear, her brother must have inherited all of the idiot. Wait, what? Where's the truck? Oh, don't tell me it's been jacked. Jesus, give me a minute. What a mess. Hold on. Searching cameras in the area. Lester don't give up that easily. Got it! Just some stupid opportunists. Sending you a live location. Chase them down and get the stuff back.
She's skating beautiful, but she's skating so fast. She's never like the girl from once I knew.
Nice work. I don't know why, but I was getting palpitations. Maybe because it was our Georgina's seed money on the line. Those arcade machines better still work. From the looks of it, those opportunists are coming back at you. Guess they must be gamers. Good work. We can play Street Crimes when you get back. It's a Degenitron classic. I remember when it came out, I was a good kid before that game glorified criminality and violence and corrupted my poor, innocent mind. Yeah, right. I've always been a punk.
It's not working. These dumbass pieces of shit. I mean, I swear to God, they're not even connected to a network. And they're busted. I mean, come on.
Are they plugged in?
Yeah. Oh.
Yeah.
What was I supposed to know about that?
Lester, you got a visitor!
Coming! Oh, you mean the owner is here, Wendy?
Yeah.
So, we're getting there, aren't we? Once we get the rest of the cabinets set up. You know, I have kill screened a shit ton of these babies, and by the time I'm done, I will do them all. Just wait till you see what we've done downstairs. We have been very busy. Hi! You remember Miss Chang?
Call me Georgina.
And Huang?
Yes, great. The place looks great. Good work.
So?
I'm terribly sorry, but we have to move along. John Pensy just ordered rosé.
What?
They can wait. Lester, you're going to say?
Yes. We were brainstorming some ideas the other night and came up with a whole new approach. When Georgina said that security is a level above anything I've encountered before, she was right. So, there's going to be 3 parts to our heist. Scoping, prepping, and the score. Except this time they're all going to be much more interrelated. You see, what you scope sets up what you can prep, which then sets up how you do the score. Depending on how hard you look, you might find one exit route, or you might find a few, which then gives you different options. Ideally, if you scope it right, there will be 3 main ways to do the job. Number 1, aggressive. Number 2, silent and sneaky. Number 3, the big con, you know, like subterfuge, and with variation on how we can pull off all of these. Like this. Are you with me?
Now tell them what we talked about the job.
Yes. Yes, I was, just getting to that. You see, with security like this, we'll need to be more adaptive. If our approach isn't working, we gotta be ready to switch it up on the fly. Before, if you were caught being sneaky, we just called the whole thing off. But now, you're going to transition to the more aggressive approach, and you keep on pushing.
It's amazing. If only we could keep on doing it. Rob it every week. I want this casino to be the anvil around Thornton Duggan's neck.
Yes, but let's start by just doing it once.
I got a text. The rosé is getting warm. Georgina, please.
Oh, Huang. If you need me for anything, please don't hesitate to call. We'll stay in town until it's done.
It's in good hands.
I mean it. Anything, call me.
Roger that. Roger that. Idiot. Okay, well, take a look at the board. And when you're ready, you know what to do.
Okay, so, you ready to scope out the target? The classic first step. Head on over there. Like I said before, how we can approach this thing will depend on what we discover at this stage. So be as thorough or as quick as you like. There's a lot of information you can gather, but it's not all equally important. Oh, and just so you know, our rich benefactor's covering the cost of this venture the first time through. If we were to hit it again, you'd need to put up the meager setup fee yourself, but she wants to make sure it's done right at least once.
purchased in a penthouse at the Diamond Casino and Resort.
You have aroused my curiosity. Mr. Mikey. You got what we need. Now you can call it a day, or you can keep looking around to see if you can find anything else that might help us when it comes to the big day. Up to you. When you're done, head outside. Okay, you made it out. That's harder than it should be. Those places are designed to trap you in and keep you spending. Now, I need to see some other exits. Can you give me a pick of a side door? I'm looking for any that have security keypads. Great. That could be a way in, too. That gives us basic coverage for entrances and exits, but there should be more to see if you keep looking. Up to you.
Still rolling down 5 flights of stairs. Word, word. We having a booty shaking contest down here. All the ladies with the fattest ass, get that donkey over here. I'm talking 2 watermelons, 2 whatever. Get that ass here ASAP and shake it for a brother.
This could work. If we got ourselves the right security outfits and credentials, we could walk right in this way. Right to the fucking vault. The art of subterfuge. I like it.
そ知らぬふりで今は言えないダダダダダダダダダダ二度と傷ついて終わらないために
Okay, I've organized my thoughts a little since we last went over this. We got 3 boards. This one covers scoping, and the intel we need to gather on casino security and what they're keeping in the vault. Vault contents. We need to know what they're keeping down there. Hack into their internal security feed to see inside. Are you a nerd about this stuff, or do you like winging it? If you want to practice for this test, we can get a copy of their door security locks made and installed down here so you can practice on them. And a model of the casino might come in handy for planning, too. Find him. There he is. I've uploaded a SecuroServe app for you to hack his phone and get those login details. Thing works well, but you'll need to stick close to get the data. Shit, he's on to you. Try and complete the hack if you can. Otherwise, you might need to put him down. Well, that went a bit wrong. Lose the heat and make your way over to the casino. Bring out your phone and search for a Wi-Fi signal we can piggyback on. And try not to look too conspicuous while you do it.
When you upgrade to VIP status, you get access to exclusive lounges, concierge, and valet services. Isn't it time you partied with people of your own caliber?
That's it, you've got it. I'm in the system now. You only have a limited amount of time in the security feed, so move fast. Find what's in that vault and sniff around for what... You might find something we can use to our advantage. you know what we're stealing, it's time to choose how to steal it. We got 3 approaches. Each deals with security in a different way. Let's take a look. Silent and sneaky. Now, I'm not meant to have favorites, but if you've ever seen me creeping into your bedroom and videoing you in your sleep, you'll know this one's for me. You gotta get in and out without being seen, avoiding or dealing with the guards. The big con. It's catfishing IRL. And who doesn't like pretending there's someone else and making a mark look stupid? In this case, we're fooling casino security. Get a hold of some uniforms and walk in there like you know what you're doing. Aggressive. Grr. This approach relies on going in hard and fast and violent and catching security on the back foot. Expect heavy resistance by the time you make your way out. Price of doing it dirty, I guess. It's a con job. Hey, you don't exactly have the gift of the gab, but you might have the ego to pull this off. Okay, if you're conning casino security, you're gonna need to create a cover story to get you in. And to get you out, too, if you want to avoid a firefight there. Take a look at this prep work and see what you want to do. Now the crew. We need them here at Mission Control, organizing everything with me. Gunmen. These guys will use their contacts to source some unmarked weapons. And if you've got the spare cash, they'll also help reduce the heat by causing a distraction during the getaway. The driver. They're gonna set up your getaway vehicle and a switcher card to help you lose the cops if you want to pay for one of those. Better the driver, better the cars they can help you acquire. Hackers, my tribe. They'll determine how long you get in the vault, so choose wisely or, cheaply. Your call. Really? Bit creepy, right? Who am I to talk? Looking sharp in that suit, if you don't mind my saying. You might remember I directed your attention to some keypads when you were looking around the casino. Yeah, if we want to hack them, which we do, we're gonna need some FIB technology from their building on Pillbox Hill. But first, I'm directing you to some pretty awful G-men with passes to get you in, thanks to your war.
Hey, I bye. Are you ready? Cool. So the goal is gold, y'all. But you want to rob the Union Depository? You gotta get in there first. Okay, get your hands on one of those elevator passes that the bougie-ass bankers use so you can sneak in. Client sent over an address of some rich food that has one. Here's the location.
So this dude with the pass ain't just a businessman. He mixed up in a lot of colorful shit with the Korean mob. Got a feeling you won't just be walking in there and asking for it. So wake up.
All right, sale time. This buyer's being a little sketchy. Doesn't want to give us too much information. Head out to that general area, and more details will be forthcoming. You there? Right. This guy, he's around here somewhere. 2 seconds. Yeah, okay, yeah. He's in a yellow, maybe an orange Camacho. Start looking and I'll see if I can get an exact location on this end.
up? Aye, bye. what's up?
Hey, girl, where the ring cat in this motherfucking town?
Shit, Kay, there ain't no roller disco in Los Santos.
Damn, that's another point for the D, y'all.
And then this shock you when I want to play this. When you play this. When I wrong you. I'm afraid for them ban me. I make them ban me.
In the sea, there are big fish and there are little fish. The same is true on land. But which are you? Isn't it time to define yourself? At Shark, we have different Shark credit cards based on your level of insecurity. Let your credit card color define you. Go on a shopping spree with a red Shark card. The great white shark is a beast of a card. Everyone in the restaurant will see it and know you are the ultimate predator. Tiger Shark is for the flamboyant spender. The bull shark for the violent, aggressive predator who hunts in all kinds of environments. Or there's the charitable basking shark. The card for the slow-moving liberal with no teeth. Shark for the apex predator.
That's not a luxury yacht.
That's not a cruise ship. That's the Blue Ark.
You upsetting.
Who's that?
Lee Scratch Perry. Clear the way, fanatics. Repent and watch and pray. Fanatics, clear the way, Sin City. Repent and watch and pray. Watch. Money comes and money goes. Money comes and money goes. But I remain. Clear the way, or phase away. Clear the way, or phase away. Money comes and money goes. Fanatics. Money comes and money goes. Aristocrats. Love comes and love goes. Human come and human goes. But I remain. I remain just the same. Hypocrites. Clear the way. Hypocrites. Clear the way. And face away. Diplomatic. Clear the way. And face away. Clear the way. Clear ye the way. And watch and pray. Money comes and money goes. But I remain. Money come and money go. But I remain. Hypocrites. Many may come and many may go. But I remain. People may come and people may go. But I remain. Love may come and love may go. But I remain. Money may come and money may go. But I remain. Love may come and love may go. But I remain. Lee Scratch Perry. Upsetter. Lee Scratch Perry. Upsetter. Money may come, money may go, but I remain. Love may come, love may go, but I remain. I remain and I remain. I remain with my iron vein. I remain and I remain. I remain. Hollywood, clear the way. Hollywood, clear the way. Hollywood, clear the way. Clear the way, I'll fade away. Money may come and money